Okay. Good morning, everyone. Yeah, I just want to run through your chapter 3, which is what you have in your modules. Now, with respect to chapter 3, which is related to fundamentals of concrete, it's concrete binders material, which is binders of cementitious material. And in these slides, you have the history of concrete, and that's, you can see the stones around. So yeah, now then after that you have the lime cycle, which is the limestone cycle. Here you have calcium carbonate, and you have calcium oxide, you have calcium hydroxide on this side. Now when you draw the lime cycle, which is preferable that you do it in this way. At the beginning, you would have what you call, at the beginning, on this side, you have a limestone. So that's a limestone, which is calcium carbonate, which is represented as CaCO3. So uzambhala kahle la CO3, CaCO3. And how does it work? Now you have your lime cycle. Then after your lime cycle, you then have your what you call your, on this side, your calcium oxide, which is represented by CaO, that is calcium oxide. How do you achieve the calcium oxide? At this point, if I can draw using the lines to get the calcium oxide, there is a need at this point, maybe that you put the heat on that stone, limestone. Once you put the heat on the limestone, then it's heated at this point by, it's heated by, that is 1450 degrees Celsius. So you use degrees. I think I have degrees here in my symbols. Where is the degree? Not here. So you put degrees. You put that in degrees. That is degrees Celsius. That is degrees Celsius. So that is under heat. With 1450 degrees Celsius, and you get the calcium oxide. What is the calcium oxide? It's known as a lime. Is known as the quick lime. Quick lime, that is your calcium oxide. When in your quick lime, that means this one, it's a stone, then you heat, then it breaks, therefore it becomes a quick lime, which is now now once you get the quick lime, then you add water on the quick lime. If you would put that on this side, we add water on the quick lime. Add water. So there's an addition of water. So we can represent that addition of water and say add H2O plus H2O. Write that H2O in a correct manner. That is water. You add water, H2O. Then once you add water, then you will then get a slake lime. What is a slake lime? It's something that looks like a putty, a boy putty, that one that you use to fix the windows. Therefore, you get the slaked lime. Slaked lime, which is the slaked lime adds calcium hydroxide. Calcium hydroxide, Ca. Then you have that OH, because there's an addition of water, OH. Therefore, you have that 2, which need to go maybe a little bit below here. So you write that H2O in a correct way. Therefore, that's your slaked lime. Then you put again, that's how the lime cycle, if there's an addition again of water and that's calcium hydroxide. So you add more water, that means you achieve lime water. That means you achieve lime water. In your lime water, just give me a second. Thank you. So if you add more water, you achieve lime water. That means it will be more wet than slaked lime. Therefore, you get lime water. This lime water. Which is indicated by calcium hydroxide as well. It's CaOH 2, which is that OH2, it's a lime water, which is indicated by AQ. So it's indicated by AQ. So that's what you have. Then once you remove the water from this lime water, you then get the limestone, because what happens if you remove water, which is called carbonation. Therefore, you then get that is carbonation, which is CO2. So that is CO2. You write that CO2 in a correct manner, of which this is known as a limestone cycle. Limestone. That is your limestone cycle. So when in a question paper, or you get a question and being asked to draw a limestone cycle, I'm expecting that you draw a limestone cycle in this way. Okay, so you draw a limestone cycle in this way. So that's what you do. That's what you do. That's what you do. So to carry on with the slides, so you got the limestone cycle. And you can see you got a Roman concrete made of the Romans made concrete which is hardened underwater by mixing lime cement, which is volcanic ash. So there is also a building, that's a history of concrete. Now, the manufacturer of Portland cement, which you have the limestone, which we spoke about, limestone, which is used to make Portland cement. Now, and shale, which is clay, mined, crushed, and blended together in a critical proportion and milled together to form a raw meal. That means you burn those under 1,450 degrees Celsius. I think I spoke about that. And the clinker cooled down rapidly, and the clinker ground with about 5% of gypsum, which is, I spoke about a gypsum, which is the quick lime. I've said that it looks like a patty, and the gypsum also looks like the patty. You have this terminology that we will use often, which is, for instance, I might ask you, what is tricalcium silicate, which is abbreviation, it's C3S. And you have dicalcium silicate, which is C2S, and tricalcium aluminate, which is C3A. And you got tetracalcium aluminium ferrate, which is C4AF. So these are the abbreviations that you might be asked on what does that mean. There's a more range of the composite oxide. You have this one, SiO2, that's a silicate. You have that as you go on. Then the hydration of cement. How does the cement get hydrated? Now, if I can come back to this one, you have these oxide, you have alumina, you have ferrial oxide, you have calcium oxide, therefore you have magnesium oxide, and you have all these. So now, the hydration of concrete, the cement goes into solution on how you mix the cement with water. Okay, then it gels, calcium silicate hydrate, which is CSH, which is calcium silicate hydrate, grows on surface, and calcium hydration will take place and also form crystals, which not for the strength. Sorry. Then you got water is assumed to be a chemical reaction, which is if you put water in your concrete, which is a mixture of your sand, cement, and stone. So therefore, it will then react with the cement, and that water, once it reacts with the cement, it will melt the cement with the stone and also the sand and form your concrete. And the hydration then will take place once you pour your concrete, and you'll see that most of the time the water will rise in some instances. Then below the water, which now the water, if there's the sun, it might act as a protection to the concrete. So there is the hydration of cement, and now you have the graph indicating the hydration of cement in hours in a rapid calcium silicate hydrate, and so that's where I want to go. C3S, which is C3S. We spoke about C3S at this point here, I think here. C3, that is tricalcium silicate, and the second one is dicalcium silicate. So this one is tricalcium silicate, hydration, heat under heat of hydration. It has high strength. It's high. There's a heat in that one, and in dicalcium there is a low heat, and this one, that is what you call tricalcium alumate, you get a high heat in that one, and this one C4AF, you got a medium one. Now, when it comes to the effect of that, early strength, how early does it get the strength? How early the concrete that you under with that tricalcium? Therefore, it's good, the early strength. And the late strength, that once you reach the 28 days, we're working on that. Once you reach the 28 days, which is the target, at the 28 days, you should reach the full strength of your concrete. Now, it's good. And when it comes to dicalcium, I think Ca, that is dicalcium, it's poor early strength. It takes time to harden that one, and it's excellent, which is very good at 28 days, or after 28 days it becomes very strong. This one, tricalcium alumate, it's medium and poor at the later stage, and this one, it's poor and poor. Now you will see there's a graphs indicating the contribution to heat. Therefore, you can see here, and also if you move to this one, now you see this one, the strength for this one, the tricalcium, it grows as time goes. And this one, it grows, and maintain the level. This one is dicalcium, this one is tricalcium, which maintain the strength. And these two, they are not good for the use of in concrete. Okay, so you also get the hydration continues, and approximately 3 hours dominate period of the gypsum. The rate increase rapidly. Hydration continues as long as there is water and moisture. Therefore, the heat and the rate of hydration are reduced with less. This one is tricalcium and alumate and tricalcium hydroxide, silicate, sorry, and you have that means the hydration continues as long as there's water and moisture, which is heat and rate of hydration are reduced with these two. The fine cement reaction reacts more quicker when you have a fine cement. Therefore, it will react more quicker when mixed with water. Now, you go to cement extenders, which is one of the very important points that we need to look at, which is you have a slag from Newcastle. So you have fly ash, and also here is your extenders, which is fly ash, slag, and condensed silica fume. It's very important that you understand these extenders, these cement extenders. So now here is the fly ash, which is ash resource. That's how it looks. And you have the fly ash. It's extracted from chimney of the power station, firing pulverized coal and or pozzolan that reacts with calcium hydroxide and not water. Is the chimney where you get the fly ash. Typical fly ash particles. Here you can see fly ash hydration produced after 28 days. And fly ash advantages, it's very important that you know the advantages, which reduce the material cost, improve the workability and cohesiveness of the concrete that you're mixing, less mixing water for equal, consistent, and round particles, cheaper with improved workability, less heat arise, low permeability, thus more durable concrete. It improves the resistance to chemical attackers, chloride attacker alkali silica reaction, which is now it improves that. If you're mixing the concrete, sometimes there could be chemical attackers, which you don't want those chemical attackers to reach your steel inside your concrete, because once that chemical attacker reaches the steel, that means the steel will rust. Once the steel rusts, that means the concrete will start cracking in the building. I believe you have seen such buildings. And the disadvantage is additional. It has an additional cost of storage and handling. It takes longer to cure. Meaning that if you mix that into concrete, you strip that concrete very later. It will take time for you before you strip the concrete. You have the slag. You can see the back of the slag. It indicates slagment, ground granulate blasted fume, which is the slag for. Now, it's produced by the iron. It's a product of the iron, which is the slag is rapidly cooled down and mild, reacts with water in high pH environment, forms calcium silica hydrate as with cement but not CH. Now you can see where does that comes. So yeah. Now GGBS with hydration product, therefore you can see that. You can see the pictures of it. That's not important. The advantages of the slag, it's less cost, lower temperature rise, better chemical, chloride and alkali resistant, which is the same as fly ash. Disadvantage, same as fly ash. It takes time to harden, meaning that you strip later. It costs in terms of the storage. Therefore, you get condensed silica fume, which is your condensed silica fume. That's a picture of that. It's produced by ferrosilicon furnace, and there's SiO2 is formed as a vapor and condensed. The powder is then densified and very fine, and it's twice as fine as tobacco smoke. So it comes from also pozzolan that reacts with calcium hydroxide. Advantages of that, it replaces 3 to 4 times its own mass. Better cohesion, less blending, less permeable concrete, better ASR resistance. Low bulk density, that's your disadvantages. High water if more than 5%. Low blending could cause plastic shrinkage, which is it could cause cracks in your concrete. It's known as plastic shrinkage. South African cement, if you look on the South African cement, new standard introduced 1996, and based on the draft, and then that is, I'm not interested in this, and you get this OPC, RHC, these are the types of cements, and common, I'm not interested in that, common cement, mensural cement, other. So now, if you look on this table, now, firstly, here you have Portland cement, you have Portland cement, slag cement, Portland silica fume cement, Portland pozzolan cement, you've got these cement. Now we have here SEM1, SEM2, SEM3. Now what happens here is, for instance, these are cement extenders. That means Portland cement, it has a clinker, 95 to 100% clinker. And this one, SEM2A, it has clinker of 80 to 94%. It has blast fume slag of 6 to 20%. That is SEM2. That one of AB, it's 65 to 79% clinker, it has that, and 21 to 35% of blast fume silica slag. It has 21 to 35. Now you go to Portland cement silica fume cement, which is in the SEM2A to D, which is 90 to 94% of the clinker, which it does not have the blasted fume, but it has silica fume of 6 to 10%. So that's how you read this table. As you can see here, SEM1, SEM2, SEM3, SEM1, Portland cement, blasted fume, that's SEM3, pozzolan cement, composite cement. A, B, or C indicates the level of extenders. In cement, A is 6 to 20%, as you can see here, A at 6 to 20%, for B is 21 to 35%, here is indicated here. Now, here are your SEMs. Again, SEM1 is pure Portland cement. Therefore, SEM2 has low extenders, while SEM3, it has, that's 1, 2, 3, it has high extenders. Now, meaning that SEM1, 2, or 3, 1 or 2 letter, that means there is extenders. That means there's a low, maybe low GGPS. That means it reacts and R or N high early strength. That is indicated by R. That means that's a normal strength that you achieve under N. This one, once you put 10 extenders, you achieve a very high early strength in your concrete if your cement contains cement extenders. There's a water cement ratio that I will deal with it when we're dealing with, I think it's chapter 7. Okay, extenders type, S, blasted fume slag, D, silica fume, I spoke about that, fly ash, limestone, composite, so we spoke of that, and it's a cement, it's SEM1, it is, the normal strength is 42.5, and this one is 52.5, the strength that you can achieve, it's SEM1, and SEM3, that is 32.5, with it has high early strength, and as you can see here, SEM2, which is 42.5 Portland cement, Portland fly ash cement containing 21 to 35% of fly ash. That you can look on that. 2 days strength, that's 10 MPa, therefore 28 days strength is 42.5, but less than 62.5. So in this type of cement that you have, that means it will, this 42 is indicated in your cement bag. So there is 42, that's your 28 days strength. You should achieve that strength. You have a Mensuri cement, which is this one. That's the strength of it for Untitled Chapter all. So it's 12.5. That's the strength of it, the maximum strength for cohesive plastic mortar and plastic good water reaction characteristic blend of PC and lime and limestone, and often contains air entrance. So that's that one of the Mensuri. You also have what do you call? Here is what I'm interested in. The factors to be considered when selecting a cement, which is the cost of the concrete, the 28 days strength that is required before you can select the cement, because each cement will tell you the strength of concrete that is required by the engineer. So you look on that before you can select the cement. Ability to resist aggressive, sensitively to poor site practice and extenders and other properties, do not extrapolate performance data for one cement as representing all cement. Do not assume what is permitted in Europe will work. Then you start checking your site conditions and check what is required by the engineer. Meaning that for you have to consult the manufacturer of the concrete to find out if that concrete will be suitable, that the type of which type of concrete will be suitable for your site conditions. So you got white cement, you got high aluminum, so I'm not interested in that. I'm also interested in the storage of the cement, which is storage underground in weatherproof sheet. Stack bags close, avoid air circulation, first in, first out. So the first one that you put in, it must be the first one that you take out, because otherwise it will stay there for so much time. Not more than 12 high. So you don't pack more than 12 different types separately. So you check torn bags must be replaced with new bags. Cement with a lamp must be used. Floor and wall storage, shade and floor struck bodies must be free from sharp protrusion, such as split on nails and bottles. You have also the cement bag must be carried out and not dragged into over the rough surfaces, which is you might stretch the cement and cause the problem, because once it's open while it's down, it will react, meaning that it could easily react and get hardened. So scaffolding, you lift that high. Workers wearing boots should not walk over the cement. There is a bulk cement storage, which is a silo tank. Keep inspection, covers properly sealed, replace damaged and blocked air filter, mark silo filling pipe clearly with cement or extender type. So advantages of the silo tank is that it's cheaper price of per ton, no handling and storing, because you put your cement, it goes into your silo tank, your cement, and weatherproof. So there is no theft that could happen in terms of people stealing the cement on site, less wastage, and that comes to the end of this slides. I've run very quick in these slides. I believe you will be able to get through that. And yeah, now what is going to happen? I'll share some of the previous question papers that were dealt with. Then you look up to chapter 3 on those question papers, of which we're writing 1, 2, and 3. So yeah, yes. Thank you.